Hello students, this is the second part of examples based on monotone sequences. We will discuss some examples from the exercises of Goldberg here. Monotone sequence is the sequence which is either non-increasing or non-decreasing. And if it is bounded, then the sequence is said to be convergent. So let us see some examples based on this. This is question 6 from the Goldberg. So here we have given that this is the nth term of the sequence. Now here Sn is, the formula for Sn is not a single term you have given, it is not a single function in n. So here numerator is the continuous product of odd numbers and denominator is the product of even numbers. That is, if we want to write down S1, then S1 is equals to 1 upon 2. That is, here if we'll put n equal to 1, then 2 minus 1, 1 and 2. S2 is, now numerator will be product of first two terms odd numbers, first two odd numbers, and denominator will be product of first two even numbers. That is 1 into 3 and 2 into 4. Similarly, S3 is product of first three odd numbers, means numerator is product of first three odd numbers and denominator is product of first three even numbers, and so on in this way. So you have given Sn is up to this. Now we have to show that this sequence is convergent. Sn is convergent. So first we will show that this sequence is monotone, and then based on whether it is increasing or decreasing, we will show that it is bounded. So first step to prove that or to show that sequence Sn is monotone. Now for such type of sequences where the numerator and denominator is product of some continuous terms, here we use this test to show that the sequence is monotone. So we will consider this ratio Sn plus 1 upon Sn, and if it is less than 1, then it is non-increasing, and if it is greater than 1, then it is non-decreasing. So let us see here. First we will find Sn plus 1. So what is Sn plus 1 here? So Sn plus 1 is the product of, means in the numerator, it is product of first n plus 1 odd numbers. So let us write Sn plus 1. Sn plus 1. So 1 into 3 into 5. So these are first n odd numbers up to this as Sn. Next will be 2n plus 1. So Sn plus 1 contains now in the numerator product of first n plus 1 odd numbers, and in the denominator it has product of first n plus 1 even numbers. So up to 2n plus 1, 2. Next even number is 2n plus 2. So consider Sn plus 1 upon Sn. Now here, by observation only, we can say that Sn plus 1 contains the full term of Sn. That is, Sn plus 1 can be written in this form. So let me write it first and then you will get it. So Sn plus 1. Now this whole term here is what? Sn. So this is Sn into 2n plus 1 upon 2n plus 2. Is it? So now, therefore, directly from this, we can write Sn plus 1 upon Sn is 2n plus 1 upon 2n plus 2. And here you can check that as n is integer here, positive integer, n belongs to I, denominator is greater than numerator. So obviously this ratio is less than 1. So this is less than 1 for all n belongs to n. So from this we can say that this sequence is non-increasing. So what we are getting? We are getting Sn plus 1 is less than or equal to Sn for all n belongs to I. Therefore, this sequence Sn is non-increasing. That is decreasing sequence. Non-increasing sequence. So here now step 2. As this sequence is non-increasing, we have to show that this is bounded below, because obviously it is bounded above, and it is bounded above by S1. S1 is the least upper bound for this sequence. So to show that sequence Sn is bounded below, as this sequence Sn is bounded above by S1. That is, Sn is less than or equal to S1. And what is S1? 1 upon 2 for all n belongs to I. Okay. But to show now that this sequence is convergent, first we have to show it is bounded below. So for this, we will here observe the terms of Sn. So if you go on writing the terms of Sn, it will be never 0. And as it is non-increasing sequence, right? Maximum means all terms are positive. So beyond 0, that is no negative term we will get. So here, by observing this Sn only, we can say that since all terms of sequence Sn are positive, and this sequence Sn is non-decreasing, non-increasing. What we can say that every term of Sn is greater than 0. Every term is positive, so it is strictly greater than 0. So we can say that this is the greatest lower bound for this sequence, and this relation will be satisfied for all terms of the sequence. So what we are getting here, 0 is less than Sn and Sn is less than 1 upon 2. So this implies 0 is less than Sn and Sn is less than or equal to 1 upon 2 for all n belongs to I. So therefore, this sequence Sn is bounded, and as this is monotone as well as bounded, what we can say? It is convergent sequence. So therefore, the sequence Sn is convergent. Now the next part in this example which we want to show is that limit of Sn is less than or equal to 1 upon 2. So here it is clear from this, if we take limit throughout, then limit of Sn is less than or equal to 1 upon 2. So let us write it. In the next part, we want to show here, they have asked in the example. Since 0 is less than, Sn is less than or equal to 1 upon 2 for all n belongs to I. Taking limit throughout, so I will not write now 0. So limit of Sn as n tends to infinity is less than or equal to 2. And hence the proof of this example. Let us go to the next question, question 7. Question 7. So question 7, it is same type of question, but here we have to prove that it is non-increasing only. No, so here Sn is given. Let us write down. Little bit different than this Sn. Just they reverse. Here in the numerator it is product of odd numbers, and in the denominator product of even numbers. Here in the numerator the product of first n even numbers, and in the denominator, product of first n odd numbers, but along with this number also. We have to show that S1 is greater than S2 is greater than S3 only about for these three terms, and we have to prove that also the sequence Sn is non-increasing. So the proof is same as this example. So first of all, we will go to the first proof, that is S1. We will show that S1 is greater than S2 is greater than S3. So it's very simple. What we have to do, just find value of S1, S2 and S3 and check their relation. So let us find S1, S2 and S3. So what is S1? So here now we have to take into consideration this 1 upon n square also. So S1 equal to S1 equal to now in the numerator here product of first one odd even number upon 1 and 1 upon 1 square. So it is 2. Okay. Then S2 product of first two even numbers in the numerator, and in the denominator product of first two odd numbers, here it is 3, and 1 upon n square, that is 2 square. So what we get here, that if we simplify here, then this is 2 square, so 2 square will get cancelled, so it is 2 upon 3. Then S3, again same way, product of first three even numbers, product of first three odd numbers, and here it is 1 upon 9. So let us evaluate this. What we are getting, here it is so any common, so here 2 and here 3, right? So 4 4 is 16 and upon 45, right? Let us check the value of these numbers. So here obviously this is equal to 1 point, I'm sorry, not 1 point, 0.66 something. So obviously it is less than 2. Here also if we find this number, then this number is equals to, let me calculate it. So here 0.355 something. So we can see here that these numbers are decreasing. So S1 is the greater number. So this implies S1 is strictly greater than S2 is strictly greater than S3. So this is the solution of this first question. Now let us go to the second question, that we have to show that Sn is non-increasing. The same way we will do that we will consider the ratio type test, that is Sn plus 1 upon Sn. So if it is less than 1, then it is non-increasing. Let us consider here. So Sn given, Sn is equal to, let me write it again, 1 to 3 into 5, 2n minus 1, 1 upon n square. So Sn plus 1, we will find S1 plus 1 and here 2, 4, 6, 2n. So first n plus 1 even number. So next even number is 2n plus 2. Here 1, 3, 5, then 2n minus 1, and next odd number is 2n plus 1. And here it is 1 upon n plus 1 square. N will be replaced by n plus 1. So let us consider the ratio of this. So we can observe here that this part will get cancelled. So let us see what happens. So consider Sn plus 1 upon Sn. So this is Sn plus 1 upon Sn. Should be at the center. Put it in the bracket. Let me put it in the square bracket so that we can identify it. Okay. Now this part up to this 2n and 2n minus 1. Here it is common and it will get cancelled. So only the remaining things are, so this will be equal to 2n plus 2 upon 2n plus 1 into 1 upon n plus 1 square upon 1 upon n square. So let us evaluate it first. Simplify. We will simplify this. Let us see. So now here, as the question is prove that it is non-increasing, we should get it is less than 1 because we have considered the ratio Sn plus 1 upon Sn. So we should get it less than 1. So let us see here. So this is equals to, using the property here, 2n plus 2, and now here 1 upon n square, this will go in the numerator. So here we will get n square upon 2n plus 1 into n plus 1 square. And now it is easy to simplify this. So let us simplify. Now from this we can take n2 common. So n plus 1 here, n plus 1 into n square upon 2n plus 1, and here n plus 1 bracket square. So here it will check 1n plus 1 and this n plus 1 here, 1n plus 1 will get cancelled. So what is remaining? Let us write it. So it is 2n square upon 2n plus 1 into n plus 1. And now again here in the numerator we are getting 2n square. Let us do the product. Here it is clear, actually it is less than 1, but let us see. Then the product is 2n square plus 3n, 2n plus n plus 1. So here it is clear that the denominator is greater than numerator. Therefore, this ratio is less than or equal to 1 for all n belongs to I. So this implies Sn plus 1 upon Sn is less than or equal to 1 for all n belongs to I. So what is the conclusion? The conclusion is that the sequence Sn is non-increasing. Non-increasing. So thus this was the second question in which we want to prove that the sequence is non-increasing. So thus we have solved these two examples of the exercise.